Hi, today we learn about the big O notations in very simple terms. So before we implement an algorithm in the code, it's important to evaluate its efficiency. This can be done answering the three following questions. Will the algorithm produce the desired result within a reasonable amount of time? How many inputs can the algorithm handle effectively? How much memory does the algorithm require? So let's start with a very simple examples. We have a function called my algorithm to find out the complexity of the function. So think of the functions like this one. Let's say this is our first functions. Uh, so we have defined the functions that assigned a value with the given parameter or arguments, and it returned the value. So what do you guess? What will be the complexity of these algorithms? If we run the algorithm here, what's the problem? Let's say, so if let's about hi. Today we learn about the algorithms, bigger notations. What does it mean in very simple terms? So before we implement an algorithm in the code, it's important to evaluate its efficiency. This can be answered by three questions. Will the algorithm produce the desired result within a reasonable amount of time? How many inputs can the algorithm handle effectively? How much memory does the algorithm require? The complexity of an algorithm refers to the number of steps and instructions it takes for a task. For example, multiplying two numbers is one instructions. If a loop is executed 100 times, there are 100 instructions. The time it takes for an algorithm to complete will depend on the processing power of the CPU, but the complexity can be used to compare the performance of different algorithms. So big O notation is a standard way of expressing the complexity of algorithm. Let's start with the very simple algorithm, which is my algorithm 1. Here we are assigning a value, very simple value with the x value, and we're dividing the value and returning the value. So what do you think the complexity of this algorithm will be? The complexity of this algorithm will be big O of 1. Big O of 1. Why? Because the algorithm complexity is big O 1, meaning it will always take a constant time to complete regardless the size of the input. If we change the size, if we change the size to 10, it will be also 1, because it just assigning the value, just one instructions in here. If we even change the value with 1 million, it will be the big of 1, because it only performs a constant number of operations regardless of the size of the input. Now just let's see our second example. Uh, let's go here, this code. Yeah. So in this example, in this function, you're uh, using summarizing a value. Okay, we are summarizing value. Let's say our n is 10. So 100. So what it does, it runs a loop from a starting point 1 to 100, and every iterations it assigns the value, it sums the value, and uh, assign the value into the sum variables, right? So if the sum exceeds 1000, the loop stops and the total sum will be returned, right? So what do you think the complexity of this algorithm will be? In this code, we have a loop that runs a certain number of times based on the value of n. For example, if the n is 100, the loop will run 100 times. The number of instruction inside and outside of the loop is not important because it's a small number. The complexity of this algorithm will be big of n, because the loop will run for n iterations, right? So the number of instruction is, so what does the worst case scenario? So the number of instructions here in this case 100. is the worst case scenario in our is the worst case in our complexity, right? Now just see, uh, so in this code the complexity of this algorithm will be big of n. And now just go to the next examples. Okay, here we are calling this algorithm uh, 3, right? So in this code what we are doing, we are summing again, but in this code we are using two loops, right? For here we are using one loop, and for the inner block we are using another loop, right? And every loop we are summing the value of these two iterations, right? So what do you think the algorithm, the complexity of this algorithm will be? So the complexity of this algorithm will be big of n square. Why? Just think a bit. The inner loop runs n times on the first iterations, right? The inner loop runs n times in the first iterations. The outer loops runs n times for the first iterations. The inner loop runs n minus 1 times, right? As you can see, the n minus 1 times in the inner loop. So the total number of iteration of the inner loop can be calculated by the adding the number of the iterations for each iterations of the outer loop. So here if we see, so, n plus n minus 1 plus n minus 2 n minus 2 plus n dot dot, let's say you're using this one, and we see the n squared by the mathematical definitions of it plus 1. We are getting the formula of this one. So it will be n to the power where is this, n to the power plus n square plus divided by 2. Okay, so this means the overall complexity of this algorithm will be O n square, because we are using two inner loop in here, right? So the constant is not a factor. In algorithm we just avoid this one. And technically the complexity should be this one. So big O of n square plus n, but n is very small here, so we are just avoiding the n, right? So this will be the complexity of this algorithm will be O times n square, because the constant factor have to be excluded while calculating the complexity, but the constant factor must be kept in mind while we are writing, right? So now just go to the next example, which is an binary search problem, right? Which is a binary search problem. Oh, I deleted the code, so let's write this code from the beginning. My algorithm 4, right? So, and it's taking a value. It's a value. Let's implement a binary search key. Let's assign the value 1. High should be n. So we are using run when low is in terms of high. Let's define a mid code here, plus low plus high. Let's define the value. If the key, the middle value of the midpoint of this low high, let's define low is the mid minus 1, right? The high is, so if the key is val mid, the high should be mid plus 1, right? If the key is equal to val mid, let's return 1, right? and let's return 0 if none is found. Okay, so this is the implementations of the binary search problems where we are dividing every search space by half, right? So in each iteration of the loop we are using here, the search space is divided by the two halves by calculating the middle index, right? You see the middle index. This process can be repeated a maximum of log 2n times, since that this is the maximum number of times a number can be divided by 2, right? So after the loop breaks, the complexity of this algorithm will be big O of log 2n, big O of log 2n, since the number of steps taken is proportional to the algorithm size, right? So for example, we are using let's say 8, right? We are using hundreds of arrays here, or values, right? So every after the loop, every iterations, the search is divided by 2, right? So it's a logarithm size of this is proportional to it is the logarithm size of the input, right? So binary search algorithm is known for the efficient performance with a complexity of log 2n, which allows them to quickly search large datasets. Now let's see another example here. So in this algorithm, we are using a constant value and arguments here. If the n is 1, return 1. If n is something, let's say n is, so in this algorithm, let's say, so it's a recursions we are using. Let's say n is 10, right? So every times the function will call itself. So the maximum depth of this algorithm is n. So the complexity, so maximum depth of this algorithm is n. So the complexity of this algorithm will be big O of n. So here let's see some similar example. The complexity of this algorithm will be big O of n square. Why? Because every times the instruction is increasing by n square, right? So we should I said earlier that we should avoid this one because those are the constant value. In this example, the complexity of this algorithm will be big O of n3, because every time the instructions or the value is increasing by n to the power 3. In this example, the complexity of this algorithm will be n log n, because we are using a log here, and we are using the log n times here. Also, the math in this example, the number of instructions will increase the size of the input size. So the complexity of this algorithm will be n times log n. In the last example, the complexity of our algorithm will be log 2n, because we are using the n to the power n here. So this is the constant. We should avoid this one. Hope these tutorials you got a good understanding of this, how big our notations or works in very simple terms.